I'm also excited to give this talk this evening. It's not a usual type of talk that I'm asked to give, and so it was fun to think about what I wanted to say, what points I wanted to kind of try to make, and I'm decided I'm going to try to show off a little bit some of the stuff that we're learning in this topic, but I also want to think of it as, in some sense, starting a discussion. So I'm going to show you a little bit of the dirty laundry. I'm going to show you some of the places where we don't understand what's going on, because really that's where the science happens, right? Is figuring out what do we need to do to try to actually understand these things that we're observing. So that said, if you have questions as I'm giving the talk, consider whether you want to try to ask them during my talk or whether you want to hold on to them and save them for the end. Because I'm hoping there will be a lot of questions, but if you ask me too many, then I won't be able to tell you the other stuff I want to tell you. So we'll find a balance. We'll find a balance together, you and I. And I'm excited to be giving a talk in this series, which is going to talk about atmospheres from the Earth to exoplanets. And I'm very excited to start with the exoplanet edge of things, because it really gives us a chance, as I say in my title, to expand our understanding of atmospheric physics into these really interesting, intriguing regimes. So, in the solar system, we have these beautiful, beautiful atmospheres, really rich physics, really interesting things going on. And a lot of work has gone into studying these atmospheres for, well, in the closer to home case, quite a while, and the farther away cases, a little bit less time. We've had a little bit more data to play with, but we have a lot of lessons we've learned. We still have some great mysteries. Other talks in this series will talk about some of the mysteries that remain in these atmospheres, but such fun, interesting places to study with really rich, dynamic physics going on. So if we focus, for example, on the beautiful, amazing atmospheric dynamics that we see on Jupiter, well, we see bunches and bunches of beautiful dynamics on Jupiter. These are all images from the Juno mission, and oh gosh, just beautiful, right? I mean, physics, but also aesthetically, this is just gorgeous, gorgeous science. I have loved this planet since I was a kid. In kindergarten, when we made paper mache planets, I chose Jupiter. So ahead of the curve there in terms of appreciating this planet. But let's think about what we can do with the interesting physics going on this planet.
What's the camera?
Juno cam.
What, X-ray, radio?
Visible. These are all visible. Yeah. Some of these they play with the coloring a little bit, but it's visible light. Yeah. So Jupiter, as you all know, sits here in our solar system. It's one of these nice gas giants that's sitting a little bit farther from the sun, in contrast to our little terrestrial planets that are all snuggled in a little bit closer to the sun. So what could we do if we wanted to shake things up a little bit, if we wanted to try to explore atmospheric physics in new regimes? Well, we could take Jupiter, perhaps, and we could smush it on down there in the center of our solar system. Why don't we smush it inside the orbit of Mercury, make it all the way exciting? In fact, let's smush it so close that if this was the sun right here, then let's put it about halfway down the auditorium. So just right there, sitting with the rest of you. That's how close I think we should put Jupiter to our sun. What would happen? It would hold on to its atmosphere. It's got enough gravity that the gravitational forces pulling down on the gas will keep most of the gas held snug to the planet. But there are some different things that we would expect to happen. The first one is that the tidal forces from the star are now very strong. acting very strongly on the planet. And what that will do is the same thing that has happened to the moon around us, is it will synchronize the planet so that its orbit and rotation are the same, and there's a permanent day side on the planet. Okay? So that's a little interesting. Permanent day side, permanent night side. Of course, we're also blasting it with light from the star, and that's going to make it hot. Ding! It's also going to drive very fast winds. The winds on a planet are generated by differential heating from the star, and if you crank up the amount of heating from the star, you expect to also crank up the speed of your winds. Because the planet is now rotating more slowly, it's locked into this synchronous orbit. Let's say it's a few days to go around the star. That means that it's also only rotating once every few days. And this means the Coriolis force in the atmosphere is weaker. And so that means that coherent dynamical flows can grow to larger scales. Whereas on Jupiter, we have all these little bands, which are jets, coherent wind flowing in one direction or the other. Those sorts of dynamical features and the vortices that we know and love should grow and become much, much larger on this planet. And here we see the limit of my PowerPoint skills. But what else? Well, the day side could become so hot that some of the elements floating around in the atmosphere, potassium, sodium, can spit off electrons. They become thermally ionized. And so you expect to have some ions embedded in an otherwise mostly neutral atmosphere. This is not realized anywhere in our solar system. And because of our permanent day sides and permanent night sides, this should not be the case on the night side. On the night side, those ions disappear. What else? Well, on the night side, or in other cool enough regions, you may form clouds. But these will not be any of the clouds we see in our solar system. The conditions are far too hot for that. And so instead, at the temperatures and pressures that we're talking about, this species that can go from gas phase to solid or liquid phase, which is what a cloud is, those species are instead salt, minerals, metal. You could have iron clouds. This is not Avatar, right? Big floating chunks of iron. This is like iron dust floating around in the atmosphere. Probably not a great place to try to breathe. But also, you wouldn't want to be there anyway to begin with. So really interesting physics that we might expect to happen on this Jupiter if we move it so close to the star. But we can do better than guess. We can add some bits of physics to what's going on. And in practice, what we need, if we're trying to describe the global circulation, global temperature and wind patterns on a planet, we know, especially from studying the planets in our own solar system for so long, that we need two main things. We need fluid dynamics to describe the flowing of the gas in the atmosphere, and we need radiative transfer because it's differential heating that drives the circulation. On the Earth, we heat the equator more than the poles, and so winds develop to try to move the hot gas from the equator to the poles. So you have to have this coupling between the two. And then there's other stuff that may interact with the dynamics and or the radiative transfer and make the picture a little bit more complicated. So we choose how we want to do the fluid dynamics, we choose how we want to do the radiative transfer, we choose if there's other things we want going on, and we put it into a computer, and we hit go, and it crashes. And we try again, and it crashes. And eventually we get it to run, and we can predict, given how we've chosen to set up the planet, what the temperature and wind structure should be all around the planet. And here's an example of some output from a simulation for this very hot Jupiter. It's sitting next to a star, and you see that the hot day side, in fact, gets so hot that it puffs up relative to the cooler night side. Okay, so we can look in a little bit more detail at some of what happens if we run these simulations. And the first simulation of one of these hot Jupiters is about 20 years old now, pretty impressive. And we see in these simulations the things we were expecting. But we see them in more detail. We had to actually solve some equations to figure it out. We see that between the day and night side, there are large temperature differences because of that permanent day-side, night-side position, hundreds of Kelvin differences. We see very fast winds on the orders of kilometers per second. Sometimes these winds are actually supersonic, which is a little bit of an issue, perhaps. And we do see very large dynamical features. So what you're seeing here is winds that are flowing eastward around the equator, and they're stretching over a huge range of latitudes, right? As opposed to the many, many little bands on Jupiter. We can add complexity, right? So this early model was just treating fluid dynamics and radiative transfer. Let's add one of those other ingredients we were talking about. If we add clouds, we actually get a fairly similar picture of what we expect with the circulation. You can ignore the red and blue curves on here. That's even more complicated stuff that I'd be happy to tell you about later. But what you can see as we're watching the simulation of the planet rotate around is a temperature structure with a very hot day side, a very cool, I mean, it's actually still pretty hot, but a much cooler night side. And you can see that there's cloud coverage all over the planet. But whereas on Earth, we get patches of clouds, here you have global scale cloud coverage because you have global scale temperature patterns. And the clouds themselves will feed back with the radiative transfer. And so that will change your heating rates a little bit. And you have interesting things like a clear region on the night side because of how the dynamics are working with the temperature structure, working with the radiative transfer, working with the clouds. All these things are coupled together in really beautiful and interesting ways. What else? What about that other thing I talked about, the ions that are sprinkled in the atmosphere? Well, now we get a different answer. In the previous slide, if I can click back, it's not running anymore, but you still have this eastward flow around the equator. You still have, I forgot to mention, the winds are so fast that they can actually pull some of that hot gas away from the substellar point, the point facing the star. They can pull that gas away a little bit before it can cool. So you have a shifted temperature pattern. But if we include those ions, which is to say if we take electricity and magnetism into account, then we can disrupt this picture. We can change what we think the winds in the atmosphere might be doing. Maybe on the day side, we pause that eastward jet, and instead the winds flow up and over the poles. Maybe the atmosphere, doesn't matter what these spaghetti lines are, but what's shown on the bottom here is that the atmosphere itself becomes so ionized that it can induce its own magnetic field. And so you get much more complicated flow patterns where you have back reactions and variability. Okay, now, as you may have guessed, this is not a purely hypothetical situation, right? We wouldn't have put all this time into just playing with an idea. There actually are these planets called hot Jupiters out there that we get to study. And that's because in the past 30 years, we have gone from, let's say, 8 planets to many, many more. And so we have the chance to take some of what we've learned about atmospheric physics in this regime and expand it significantly. If you look out at the night sky, not here in Manhattan, but like somewhere else, you won't see this, but you will see lots of stars all across the sky. And this is if we took the whole sky and we projected it completely out onto the screen. And I'm going to show you a movie showing planets as they are detected, where they exist in the galaxy. Every star that you see is a star in our galaxy. And so we start with nothing. And then as time rolls on, you start to see planets being detected. Oh, here's another one. Oh, there's more. There's more. You see the little circles where they're being detected? And as the field develops, this really starts to take off. And they're being found at a faster pace. They're being found all over the sky. They're being found by different detection techniques. That's what the different colors are. You may start to notice interesting patterns where some detection techniques are finding planets in some parts of the sky. There's reasons for that. And eventually, the number of exoplanets that have been found just skyrockets, right? Huge announcements of planets all at once, especially from the Kepler mission. That's that patch, for those who know. And eventually, recently, we passed the mark of over 5,000 exoplanets, just all over the sky. Tons and tons of planets. So a really different opportunity to understand atmospheric physics. But the first thing we understand is that if we take all of these points, all of these known exoplanets, and we put them on a plot, because we're scientists, there's quite a few different types of planets, completely unlike anything in our solar system. So each of these dots is a known exoplanet, and we've found planets with a huge range of masses. And here we have the equilibrium temperature, how hot the planet would be, just based on how close it is to the star. So it's sort of like a guess as to the average temperature of the planet. And then I've marked with X's just some of the representative planets in our solar system. There's lots of information here. There's lots of points here, but there's also lots of information, right? So one thing you notice is that here's Mercury, and tons of the planets we found are in fact much, much hotter. It's much easier to find planets that are closer to the star for a variety of reasons, and so we have a bias towards finding these hotter ones. But also, look, there's all these hotter ones. That's different. Excuse me. You'll also notice there's not so many down here near Earth. These are really hard to find. There's probably a lot more out there, but this is where we're running into the edge of what we can do. So don't worry too much about that yet. But there's a lot of planets up there near the mass of Jupiter. Right? In fact, here's our hot Jupiters that I was just talking about. Jupiter in mass, but much, much hotter because they're much, much closer to their stars. You'll also notice that in our solar system, we have our gas giants and then a gap down to our terrestrial planets. There's two types of planets, basically. Here, we see there's tons of planets in between the masses of Neptune and the Earth. That's a completely different type of planet than in our solar system. So we're seeing that the galaxy has an amazing diversity of planets in it. It gives us a wonderful chance to have a playground exploring planetary science writ large. Here are all of the planets for which we have made atmospheric measurements. Fewer points. It's very hard to do, but still a fairly significant number, right? Now I'm showing you the radius of the planet versus its mass. And again, I've labeled some points for you: Jupiter, Neptune, Earth. Mercury wouldn't be on this plot anymore. Too small. And so what's really neat about this is that we know there's a diversity of different types of planets. Here's the ones that we're measuring the atmospheres of, and there's also a bunch of diversity in here, right? Atmospheric physics and new regimes. Look up near Jupiter. These are predominantly hot Jupiters, and there's dozens of them. There's not as many as we're moving smaller. These are much harder to study, but this space is starting to be filled in as well. And this space between Neptune and Earth, these weird planets, we're starting to fill in. So a really fun time to be studying atmospheric physics. And part of the reason we really want to do this is that just from mass and radius alone, I would say we do not know what a planet is like. From an astronomer's perspective, the Earth and Venus, same mass, same radius, very different atmospheres, right? And so planets are diverse. Planets' atmospheres are diverse. If we want to understand them, we have to stretch our understanding, and we have to take some really careful measurements. So how do we even do that? How do we measure exoplanet atmospheres? Sometimes we actually see the planet separate from the star. That's great. That's fun. Thank you when we can do that. And then we can just see the light from the planet and measure its atmosphere. That's not most of the planets we've detected. Most of them we never see separate from the star. But a lot of them transit, which means they move between us and the star. And when that happens, some of the light filters through the planet's atmosphere, and we get a little imprint from whatever material was in the atmosphere. Also, planets can move into eclipse behind the star, and then we lose the little bit of light that had been coming from the planet. And that's a way for us to get the planet's mission. We can do a little more. We can stare at the planet throughout its entire orbit. And so here you're seeing, as a function of time, the light that we received from the star, which is most of it, but also a little bit of extra light that comes from the planet. This is a schematic, of course, making it easier to see. And the planet passes between us and the star, and then the planet goes behind the star. But when the planet is behind the star, we're only seeing starlight. So anything above that line is emission from the planet. And this is a schematic, but this is, in fact, a type of measurement that we do. My favorite type of measurement, one of my favorite types of measurement is even a bit better, which is that we can map planet atmospheres. Can't see the planet, but we can make a map of its day side. And we do that during this time of eclipse when the planet goes behind the star. And as the star moves across the planet, it's scanning across the planet's disk. And so losing the light from the planet, the shape that that loss takes, tells you about how the light is distributed across the planet's disk. And in particular, this is one example, if you have light more spread out uniformly across the planet's disk, you get one shape, but if you concentrate it more towards the center of the planet, you steepen that shape. You also get north, south, east, west information as well from different ways of changing the shape. This is actually what got me into exoplanets in the first place, is thinking about eclipse mapping. So near and dear to my heart. And it's been done. In fact, here is a map of a hot Jupiter from the latest, greatest space telescope, JWST. These are actual data. They've been put into this lovely infographic. But these data for this hot Jupiter were used to make that map of the planet. There's a lot of weird nuance in that map. It looks kind of like an airplane pillow. It's probably not an airplane pillow. I love uncertainties in mapping. I love thinking about spatial patterns. If you want to geek out with me about null space and degeneracies later, please do. Here is one of the plots from that paper showing the actual temperature of the planet related to its brightness as a function of longitude. So here's the point facing the star, and now we're going towards one edge of the planet and the other edge of the planet. There's pink and blue lines because there's two possible solutions to the data, because life is never so simple. And then there's some models here for comparison. There's a lot of information, there's a lot of wiggles. The important thing to take away from it is that if you look carefully, the lighter green and lighter purple lines, these are from models, have the brightest region shifted a little bit away from the substellar point by those jets that I mentioned earlier, and the night sides are a little bit warmer because of those jets that bring heat to the night side, versus the darker green and darker purple lines are models in which there is a form of drag slowing the winds. And in those cases, the brightest region stays aligned with the substellar point and the night sides are cooler. And the reliable part of these measurements is that you have this sharp gradient in brightness from the day side to the night side. And it agrees better with these models that have some strong drag in the atmosphere. And so for this hot Jupiter, we think that we're seeing evidence of some form of drag, physical drag in the atmosphere that's slowing the winds and changing how the heat is transported from day to night. And I got to be involved in the press release, so I said, use this flow that goes up and over the poles. It might be this magnetism, these ions that we were talking about earlier. Interesting, fun. What else? Let's go back to these phase curves. That's what this type of measurement is called. Because in this case, we see not just information about the day side, which we get from the map, but we also measure emission from the night side when that part is facing us. So we get to see all around the planet. These are data from the Hubble Space Telescope of a particular hot Jupiter, a different one. And they're noisy, but you can see more emission when the day side of the planet is facing us, and basically nothing when the night side is facing us. Very, very dim, weirdly dim. And when these data first were published, the interpretation was, oh, this planet has clouds on the night side. Clouds will trap some of the light and make the night side dimmer. Cool, but it's a guess. So then, we have the Spitzer Space Telescope, which also took some measurements of this planet, and also pretty noisy data. But these data also were consistent with models of the planet that had cloudy night sides, but not ones that had clear night sides. And that's what some of these lines that are here are shown for comparison. The ones that match the data better match the data. It's very noisy, isn't it? They have clouds. Now enter the James Webb Space Telescope. Well, I'm going to show a reveal. So here's the Spitzer data, and I'm using it to block out what I'm about to show you, which is the JWST data. And this paper actually appears on the archive tomorrow, I think. It's under review right now, but should be published soon. JWST is so much better than Spitzer. Let me show you why. Oof, beautiful, beautiful, right? Can we go back? I think so. Noisy, noisy data, a momentous, amazing measurement. Just beautiful data, absolutely gorgeous data. And the really neat thing about JWST is that it could give us more direct insight into the clouds because these data include wavelength information. And so you get a spectrum of the planet when the day side is facing us, and you get a spectrum of the planet when the night side is facing us. And as I assume many of you know, when you have a spectrum of an object, you know more about the composition of that object. So let's dig into this a little bit. This was a community effort analyzing these data, which was really neat to see. And so from all around the world, people contributed models to compare to the data. The data are shown here in black. And what you see are people who contributed GCMs, 3D models, that were clear for this planet, or ones that had clouds. And first of all, they don't all agree with each other. We'll sort of come back to that. But the clear models in red have way too bright of a night side. That's nothing new. That's what we knew from back before, Hubble, Spitzer. The cloudy models match the data much better. Not all of them, though. Right? If you look at any particular blue line, it doesn't necessarily match the data. Okay, but what do the spectra tell us? Well, if we look at the spectrum from the day side of the planet, we can see the data there in black compared to these models, which are all the colorful curves there. The dashed or dotted curves are the ones with no clouds, and the solid lines are the ones with clouds. They actually sort of all look good. There's some vertical offsets, that's a different issue, but they all show these spectral features, mostly due to water in the atmosphere. Water vapor, right? There's no oceans going on here. But that's because even the models that have clouds, have the ability to have clouds, also predict that the day side of this planet should be clear. So what about the night side? Here's what the spectrum from the night side looks like. And the most noticeable thing about it is that it's fairly flat. Not perfectly flat, but it's fairly flat. And you see that the cloudy models also predict fairly flat night sides, because clouds generally just dampen spectral features. So we have pretty good evidence now that our hunch that the planet's night side was so dim because of clouds actually does seem to be what's going on with this planet. We're not sure what these clouds are, though. None of the cloudy models match exactly. More mysteries. And if I'm being completely honest, you may have noticed, none of the models actually match the data, right? Oops. And even here, these models don't match this data either. We're seeing interesting evidence of this new type of drag in a planet's atmosphere, and evidence of cloud species unlike anything in our solar system, but we're not doing it right. We're getting it wrong. This is one of these places where we need to figure things out better. So, why is this a hard problem? Why are we getting it wrong? Let me list the ways. It starts with physical challenges, right? So we're solving fluid dynamics, we're solving radiative transfer, and then we can add all these other bits of physics that we think may be like of primary importance, that are not just secondary features. We have to include them to get the planet right. Well, with the fluid dynamics, we can use the standard set of equations that we do in the solar system, but, for example, if you're dealing with supersonic winds, some of the assumptions aren't really meant for supersonic winds. Also, what are our boundary conditions? You have exchange, you can have the atmosphere connected to the deep interior. There's no solid surface, it's just gas all the way down. So thinking about how to correctly deal with that issue becomes important. You have subgrid physics that's at a smaller scale than your models can resolve. If you don't do that correctly, that might feed back onto the larger scales and you can get things wrong. In the radiative transfer, we actually understand fairly well how light travels through material, but the material may have all sorts of nuance that makes this really complicated. Getting the opacities correct for the different absorbers in the atmosphere is a challenge. We don't necessarily have good measurements of how some of these gases react to light at these temperature and pressure conditions. And the calculations to try to guess how they react are very complicated. Disequilibrium chemistry. So you can say, well, we think it's mostly hydrogen and helium. We're going to sprinkle some other stuff, some other elements in it. That's going to form some water. That's going to form some carbon monoxide. But when you have this coupled system and the gas is flowing around the planet, you can take gas that at some pressure and temperature, you think you know what molecular species should exist, and you move it to different conditions, it's not necessarily going to instantly flip to whatever distribution of molecules are correct for that new location. And so the chemistry in the atmosphere can get out of whack and changes your opacities. Clouds, If you know anything about clouds, if you know anybody who studies clouds, they're complicated. On the Earth, they're complicated. They're very challenging to get correct, and part of the reason for that is that cloud physics couples the smallest scales, microphysics, how do you actually change from that gas into forming a particle? Does it collect on something else? What shape does it form? How does it grow? To the very largest scales, because of this feedback between the thermal structure of the atmosphere, the winds, and the clouds themselves. So it's an incredibly challenging problem. And when I mentioned ions sprinkled throughout, when I mentioned magnetic effects, that means magnetohydrodynamics. Not just fluid dynamics, but magnetohydrodynamics. And for those in the know, this is a situation called non-ideal magnetohydrodynamics because it's not a purely conducting plasma. So some of those annoying extra terms where you have to take into account that your currents can't just flow freely through the material matter very deeply here. Your day side is ionized, your night side not at all. Very challenging. Fun, but challenging. And then there's a bunch of numerical challenges. And I feel like if there's anywhere that you can talk about numerical challenges, it should be at the Simons Foundation. So here we go. What are some of the numerical challenges? Well, in order to model these atmospheres, you have to model across the entire pressure range. Pressure is our vertical coordinate. You go from low pressures high in the atmosphere to high pressures deep in the atmosphere. You have to model across a huge pressure range because you need to include the part of the atmosphere where all the starlight is being absorbed and the part of the atmosphere that's emitting to space. And for hot Jupiters, that covers a very wide range of pressures. And you can't just put your bottom boundary too high because you need to have that exchange with deeper gas in order to correctly treat exchanges of angular momentum. But the very lowest pressure levels that we're modeling have incredibly short timescales. The winds are incredibly fast, short dynamical timescales. The gas heats and cools incredibly quickly, short radiative timescales. And when you run numerical simulations, you have to run short enough time steps that you don't have gas jumping from one part of your simulation to the other. You need to resolve that flow. Meanwhile, at the very deepest pressure levels that we have to include in our model, the timescales are very long. And so if you start your simulation, you need to run it for long enough that the deepest levels can figure out what they think they should be doing. And so you need very short timescales, high in the atmosphere, and then you need to run the simulation for so long that you can capture whatever those deep levels want to do. Tough. Accuracy, this is sort of related to physical challenges, but it's the numerical part of it, right? Are you treating the different physics correctly? Is your numerical algorithm getting the right behavior that you want it to? Boundary conditions, I think I had that under physical challenges, but it's also a numerical challenge. You have to make sure that you don't have waves bouncing off the top of your atmosphere when there's not really a top of the atmosphere and going back down. You have to figure out, should you put some kind of drag at the bottom of your atmosphere to treat exchange with deeper levels? How strong do you set that? Do you put some convection at the bottom of your atmosphere? It should turn convective at some point. These details can matter, and they can matter numerically as well. Stability. I have a new grad student in my group, and he's going through what everybody's gone through, which is he's trying to run some of these 3D models, and they just crash and crash and crash. And all of us can give him advice, things to try, things to make them work, but there's some amount of babysitting that has to be done to get the models to run, and that's just because you can run into these numerical stability issues, especially with all these short timescales, extreme conditions, sharp gradients. It's a bit of a nightmare. And so all of this can mean very computationally expensive models. My group's models are some of the least computationally expensive in the field because we make some simplifications with our radiative transfer, and it can take a few weeks to run a model. Other models can take a lot longer. That's not all. There's other reasons this is hard. And that goes back to the point I made earlier, which is that planets are diverse. And so really, if you're trying to model a particular planet, you don't know how you should set everything in your model. You may know its mass, you may know its radius, you don't know how metal enriched it will be. So you don't know how much extra elements beyond hydrogen and helium you should dump into the atmosphere. That will change the overall opacity. We know that a higher metallicity, because of this higher opacity, leads to a larger day-night temperature difference. It has a consequence. Maybe you should test it. So there's a lot of diversity that needs to be explored with these models as well. So it's a hard problem. Okay, but I'm arguing with myself here on your behalf. You may have noticed that I said that the first hot Jupiter simulation 3D model was from 20 years ago. So yeah, it's a hard problem, but we've had 20 years to work on it, right? Why haven't we got our act together a little bit? And so here I think that we get a little bit to like the sociology of science and how fields develop scientifically. And it's very much often driven by observations. So I'm going to focus on space-based observations I have thus far. There's really cool stuff going on from ground-based facilities as well. I'm sorry I don't have time to tell you about it. But the space-based examples tell the story as well. So you may have noticed before when I was describing phase curves, I showed you some data first from the Hubble Space Telescope and the Spitzer Space Telescope. And these space telescopes contributed wonderfully to exoplanet science, but were never designed for exoplanet science. And so the level of measurement that we needed to make was often at the same level as the instrument systematics. Very challenging measurements, very noisy data. Remember those phase curves? I could fit 1 billion models through any of those phase curves, right? So why run so many? It's not helpful. I don't know what's going on. I have some guesses, but I don't really know. In comparison, we now have JWST. And this telescope was designed with exoplanets in mind. A lot of other astronomy as well, but exoplanets is part of it. And it's just larger. Larger telescopes are better, more sensitive. Also, if you've noticed, I turned the other telescopes black and white, and JWST is in color because we have much more spectral information with JWST. And that's really important for understanding what's going on with these atmospheres, because as I said before, that spectral information gives us a bunch of extra insight. So what has happened over the last 20 years is that when we took observations with Hubble or Spitzer, and we wanted to compare to our models, first of all, most of the data sets didn't really need 3D models. You didn't have access to that much information in the data, so it wasn't worth it. The phase curves, yes, you have a day side, you have a night side, you need a 3D model, but remember at the beginning I said when you have transit, you have light filtering through the atmosphere, if you just have eclipse, you have emission from the planet. The data weren't sensitive enough to see the imprint of three-dimensionality in those data. So papers comparing to these data sets, I went back and checked a little. There's never really usually more than about a half dozen 3D models compared to any of these data sets because it's not really worth it. But with a half dozen, you can maybe say something about it being high metallicity or not. Maybe you test some other parameter. Now, with JWST, things are really changing in a way that I'm excited about and also like really makes me nervous a little bit. And that's because 4 data sets of hot Jupiters, which are especially three-dimensional objects, right? These huge differences from the day side to night side all around the planet, it turns out that it might be that basically all of our data sets for hot Jupiters need three-dimensional models. Even just those transit spectra, we may already be seeing hints that one edge of the planet is different than the other edge of the planet because we're seeing multiple components in the integrated spectrum. Okay, all planets need a 3D model. And the data are precise enough. You saw we weren't matching any of the data. I wasn't surprised. I think we need to run over 100 models I think, at a minimum, if we hope to be able to actually match the data, because there's so many things that we need to try. So this is really challenging, and a change in how our field is operating in terms of understanding these planets. So in my last few seconds, I'm going to guess where I think the next 20 years are headed. We think JWST, hopefully, can run for 20 years, which is amazing. And so observationally, and again, there's wonderful ground-based stuff. That's a different talk. But observationally, I think that some of the kind of initial measurements we've been doing for hot Jupiters, I know we're already doing for some of these cooler, smaller planets. So the way that we've been exploring how atmospheric physics is being stretched into this new regime of hot Jupiters, we're going to start to get some of those hints now for other types of planets as well. And then with hot Jupiters, as I said, we're transitioning to a phase where the data are so precise that the level of complexity we can access has just taken a leap and bound. So we're going to have a lot more information. Numerically, I don't know how we're going to do it yet, but we're going to enter a regime where if we want to get at that level of complexity, we need to really amp up how many models we have, how we're exploring the parameters, how to digest all that information, how to compare it to data. It's going to be a real challenge. And I think, my hope, is that once we start running that many models, we will find some that match. We will be able to start to pin down some of those physical and numerical uncertainties that we've had thus far. And so we will be studying hot Jupiters at an incredible level of detail, and as a population, we'll get that diversity of possible atmospheres as well. So let's go back to Jupiter. The beautiful images of Jupiter, the beautiful atmospheric dynamics, atmospheric physics going on here. We will never measure exoplanets this well. But we do not yet know the limit to how much detail we can measure for exoplanets. And one thing that has been interesting to me for my entire career is pushing that boundary farther and farther, figuring out how to get even more and more information, complex information out of these data. We don't know what that limit will be. I think we can always do a little bit better. And we do know that both within our solar system and beyond our solar system, there's an incredibly rich diversity of atmospheres to study, to stretch our physics. And I would argue we need to do that in order to help contextualize our own atmosphere here at home and feel more confident that we can really say we understand how atmospheres work. Thank you.
Thanks very much. So we have time for questions. Just one reminder is to use your seat mic when you ask your question. So questions for Dr. Rauscher?
Can you hear me okay? All right, so the reason why I asked you that was that we have sometimes, in science, we forget to say, is it, gamma rays, X-ray, ultraviolet camera, visible, infrared, microwave, and radio. And amazingly, our students still graduate in science without understanding that those are different photons, different wavelengths, et cetera. So it says here that the microwave radiometer and other and infrared views of Jupiter are common from Juno. So
Yes.
That's why I asked you. Is it a composite? Is that what it's doing?
No, they're different instruments. Yeah.
They're different, so they're
Yeah.
pictures from different instruments.
Well, they don't usually make pictures from
Okay.
like their microwave measurements, but they can get like distributions of
Okay.
different species in the atmosphere.
How come we don't do more control studies of looking at the Earth's atmosphere, measuring a certain spot, and then verifying that we have accurate telescopic prediction of the atmosphere content over and over again?
No, we do actually.
So that we have adequate controls, because sometimes in astronomy, you see gigantic distances without error limits, you see predictions without error limits, you see the same thing in evolution. It occurred 4 billion years ago on February 6th at 2 o'clock. You see this, no error details. So it seems to me that we haven't done enough controls. No, that's
One interesting thing that's going on in exoplanets is people are anticipating the future space missions that will be able to measure the atmospheres of Earth-like planets. And one way that they try to get at this issue of how much can we trust that we're interpreting our data correctly is that there have been cases, and people continue to argue for cases, where we take spacecraft in the solar system that are usually meant for some other investigation and have them turn back and look at the Earth and try to observe it using some of the techniques that we use for exoplanets.
I haven't
To
seen
try
those
to capture.
publications. Where are they published?
Come talk to me afterwards. I can try to point
Okay.
you to them.
All right.
Great. Other questions? We'll do back row and then.
Hi. I love that visualization showing the gradual discovery of the 5,000 exoplanets, and notice that they're pretty much all off the galactic plane, assuming the galactic plane is just garbage because dust and you can't actually observe anything. Are there
Unless
any?
you love dust. Some
Yeah,
people love
unless you love
dust.
dust. Are there any assumptions you make about the types of solar systems that can or would exist, like way off plane like those, that would skew the data versus what you would imagine? I mean, we happen to be on plane, and that's great. I wonder how much that influences the types of systems you imagine when you're picturing like the, how often you might see a hot Jupiter on these.
Yeah. So what comes to mind for me, if you asked a different exoplanet person, they might give you a different answer. But what comes to mind for me is that the stars distributed around our galaxy, especially the ones near the disk compared to farther away from the disk, can have different characteristic ages. And I didn't point out here that the different colors are telling you different types of stars that all these planets are around, cooler stars and hotter stars. But people also think about planets and planetary systems around younger and older stars, and how you might expect planet formation to function differently if the star was formed earlier in the universe where there's less metals, or more recently. And then also the other thing about kind of distribution around the galaxy is that kind of how, whether you have a lot of nearby stars, I mean, nearby is a relative term, but whether you have to take that into account when you're forming the planetary systems. If all the stars are forming very close together, maybe they work to disrupt some of the systems, and so you never end up with planets in the first place.
As I understood, there's no kernel in your hot Jupiter. Do we know this for sure?
Sorry, there's no
Kernel, there's no solid grain in the planets? Because
at the center of the planet.
yes.
So there's probably a core somewhere very deep down, but part of the reason we think that is if you take the mass and radius of the planet, you can tell it's not just pure hydrogen, helium all the way through. And so generally we think there must be some kind of core. I was going to say similar to Jupiter, but current understanding of Jupiter is that the core actually may not be this solid thing at the center, but seems to be kind of remixed up through like the inner half of the planet.
Thank you. My question was more, could there be a magnetic field that will be coming from this kernel that will be completely decoupled in the sense its origin is decoupled, but then you will have magneto-hydrodynamics due to that external magnetic field, and that will affect, I suppose, the fluid dynamics?
Yeah, thank you. Thank you for that question. That's generally what we're thinking. Because magnetic fields seem to be well generated within the cores in our solar system, we are just assuming that they should, well, we're not just assuming, some people also like run simulations and work on this, but we think hot Jupiter should have similarly global magnetic fields generated in their cores. And so then what's happening in these instances is you have the ions that are reacting to that global field. Maybe if you're ionized enough, you start to generate your own component, but it's generated by the magnetic field. And something you didn't ask, but I'm going to add to your question, is often when we start with a magnetic field, we make it a dipole, because that's nice and simple. But most of the magnetic fields in our solar system are not actually dipoles aligned with the rotation axis. They're often maybe a little bit tilted, or Uranus and Neptune have wacky magnetic fields. And all of this gets much, much, much more complicated if you change that overall global geometry.
Great talk. On the subject of magnetism, still, so you've got these ions, and you've got a fast wind, and now you may have some core sources of magnetism. I know this is extraordinarily complicated, but is there any interest in studying the possible effect of the star's version of the solar wind on the?
Yeah, people think about that for sure. There's multiple ways that the presence of a magnetic field on these planets could show up in different kinds of observations and could physically shape the system. Those are actually coupled, right? It shows up because it affects the system somehow. And so I think about how it shapes the circulation, but absolutely, especially because you're sitting so close to the star, you may expect some significant interaction between the stellar wind and a planet's magnetic field, and you may expect also some back reaction of the planet's magnetic field on the star's surface and the magnetic shaping that's going on there. So people look for star-planet interactions to try to get at this. People look for bow shocks, which is that movement through the stellar wind, and the magnetic field could shape the nature of that interaction. And people look for auroral emission from hot Jupiters.
Right.
These are all very hard to do, and there has not been so much conclusive evidence of this, but brown dwarfs, which are very close to planets, very recently there's been detected some emission from a magnetic belt around a brown dwarf, which is pretty cool.
Thank you.
So I know we had a question stacked up back here, and then we're going to go to Megan, and then we'll come back.
Aside from transits,
Other detection methods?
like wobble, gravitational.
What would you like me to comment
Well, I mean,
about
can
them?
this be done with other types of detection methods of exoplanets?
Oh, atmospheric characterization, you mean?
Yeah.
Yes, okay, I got you. Yeah, so the transits using transiting planets and exploiting these ways of separating the planet out in time, the planet signal out in time, has been one of the best ways to measure atmospheric characterization. But I love that you asked this question because it gets to my favorite ground-based technique, which is if you take a high-resolution spectrum of the system, you have the star, which dominates, and you have the planet spectrum, and because the planet is zipping around in its orbit, that means that its spectrum is Doppler shifted relative to the star, much more than any Doppler shift in the star. And so you can use this technique to pull out information about the planet's spectrum through its velocity difference from the star. And if you do it at high enough resolution, that means that the information you're getting about the planet's spectrum can measure the shapes of the lines in the planet spectrum so well that you can be sensitive to kilometer per second speeds, which means that it's not just the orbital velocity that shows up in the data. You can also get those atmospheric winds that I was saying are kilometer per second speeds. They can shape what you're measuring from the planet.
Okay, this is a great time to go to a question from Dr. Megan Bedell, who's actually one of the experts in that technique that was just.
Little bit about the potential time variability of these hot Jupiter atmospheres. And in specific, say that I took a JWST observation of a hot Jupiter today, and then I did it again in a year or a decade. Do your models predict that the observations would look different?
Probably not, but I'm hesitant because there has been very little work empirically constraining variability of hot Jupiters. And our standard models that don't have any of that extra physics in them generally predict basically no variability. There's been a recent paper actually quantifying how very little variability you expect if you don't include any of this extra physics. But clouds give you another possible timescale that can be interacting with what's going on in the atmosphere. Diana Powell, who's one of the leading experts in cloud modeling, says that clouds should evaporate and dissipate very quickly, so maybe it's not so much of a concern. But all this magnetism stuff definitely is an avenue to possibly induce variability. So if it's a hot enough hot Jupiter, then maybe.